Hello everyone, my name is Kadir Gumish and welcome to my presentation on the topic of low-rate protograph-based LDPC codes for continuous variable quantum key distribution, a paper authored by me and co-authored by Laurent Smale for ISWCS 2021. As many of you may have noticed in the past couple of years, many advancements have been made on the field of quantum computing, which brings forth exciting new prospects. However, there are also concerns in regards to security, where in a post-quantum world or current security methods may break down. It is therefore imperative that we work on new security methods such as quantum key distribution, shown over here, which still work in a post-quantum world. We are specifically going to be focusing on the reconciliation part of quantum key distribution, shown here in red, which is where the error correction takes place. The error correction quantum key distribution requires codes of really low rates because of the low operational signal-to-noise ratio of a quantum key distribution system. These codes also have to operate very close to capacity with a relatively high frame error rate. But however, not too many code designs are available for this low rate regime. Recently, good codes have been introduced by Jose Mani, but we still don't have an easy method for designing a new low rate code of any arbitrary rate. In this presentation, we're going to be focusing on protograph-based LDPC codes. A quick recap of these codes. A protograph-based LDPC code is simply an LDPC code which is defined by its protograph, where a protograph is a tenor graph with multiple with parallel edges between check nodes and variable nodes. In the proto matrix of a protograph, the columns represent the variable nodes, while the rows represent the check nodes. The numbers next to an edge represent the amount of edge connections between a particular variable node and the check node. We can get from a protograph to a parity check matrix in the following way. We first copy the protograph multiple times, in this case 3. We then replace all of the edges with parallel edges corresponding to the number next to the edge. And we then randomly permute these edges such that there are no parallel edge connections between any variable node and check node, while still respecting the original relation set out by the protograph. This particular representation is very useful for high rate codes. However, when we go to the low rate code regime, the protographs grow in size a lot. And this makes this particular representation not as suitable for these low rate codes. Our idea was to come up with a new representation for low rate protograph-based LDPC codes in order to simplify the visualizations of these codes. An example of that is given over here. Here we have a rate 1/8 AR4A code as given by Diefsaller et al.'s paper. What you may notice of this particular code here is that several structures within the code are repeated multiple times. So our idea was, what if we, for the representation of our protograph, we simply group together these recurring structures and simply note how often they occur within the protograph. An example of how that works is the following. We first have this initial structure over here, which occurs only one time. So in our simplified representation, we also make it occur only once. We then have this second structure over here, which occurs 4 times within the protograph. So we can simplify this by simply putting a dash box around this structure, and then putting a number 4 in the corner here, signifying that this particular structure occurs 4 times. And we can do the same thing for the last structure, which occurs 3 times. This particular simplification of the visualization makes it easier to represent low-rate protograph-based LDPC codes. This also gave us an idea of how to optimize these low-rate codes. Normally, for the optimization of a protograph-based LDPC code, you would optimize each entry within the proto matrix. But what if instead of doing that, we were to predefine some existing structures and were to optimize how often these structures would occur within the protograph? So essentially, we're just optimizing the numbers in the corner of these dash boxes. The particular design that we're going to be focusing on is a design which is a concatenation of a high rate based protograph and a low density generator matrix code, which consists out of the input bits of the low density generator matrix and the parity bits of the low density generator matrix code. This particular design has been shown to work quite well for low rate codes, which is why we're going to be using it. And even in this particular design, we still notice that there are certain structures that occur multiple times. The way that we're exactly going to do the optimization is the following. We first specify a so-called type matrix. What this type matrix tells us is that in this type matrix we predefine some structures, and we then specify how often these structures appear with these V's and these C's notified over here. Once again, the columns of the type matrix correspond to the variable nodes, or in this specific case, the variable node types, and the check nodes and the rows correspond to the check node types. The V's and the C's, as I said, correspond to how often these variable node and check node types occur within the protograph. We further make a distinction between two different node types. We have our fixed node types, which occur only once within the protograph, so we don't do anything with them during the optimization, and the optimizable node types, given which are beyond the dashed lines here, which we can, and for these node types, we can change how often they occur within the protograph. So this is essentially just similar to fixing a particular type of part of the protograph while doing the optimization. So now when we do the optimization, we only have to optimize C2 through C7 instead of optimizing each entry within the proto matrix. This massively simplifies the optimization. An example of how to get from a particular type description to a protograph is shown here. We can first see that we have these fixed node types. These fixed node types once again occur within the protograph as shown here, which in this case corresponds to the high rate based protograph. We don't do anything about that because we've fixed this part of the protograph. We then notice that the second node type over here, check node type, occurs 5 times. So we also put this particular structure 5 times within our protograph. We then notice that the next 3 check node types all occur once within the proto matrix. So we make these, so we just put these structures 1 time within our protograph. Finally, the last 2 check node types don't occur at all within our protograph, so we just ignore them and don't put them in. The problem with this particular, one small problem with this particular optimization method is that for higher rate codes, the optimization becomes too restricted. One particular way of solving this is by having a so-called expanded type description. So what you're effectively doing is, instead of optimizing the protograph, you're simply optimizing an expanded version or a lifted version of the protograph. And you would have to adjust your type description for that. As an example of that is given here. This gives us more degrees of freedom and makes it easier to optimize high-rate protographs at the cost of the optimization being more complex. In order to verify how well our optimization method works, we've done the optimization for a different range of codes for both the normal type-based description and the expanded type-based description. And we then compare it to the literature. We've also done some Monte Carlo simulations to verify our results, as we will show in a later slide. So when we do the optimization with the normal type-based description, we notice that as the rate of the code decreases, our codes get closer and closer to capacity. 2 examples of our protographs are given over here for rate 1/50 and rate 1/10 code. When we do the optimization with the expanded type-based protograph, we notice that for the higher rate codes, we get an additional gain. But as the rate of the code decreases, our codes we tend to not get any gain anymore, because the size of the protograph is large enough, allowing us for enough degrees of freedom. When you compare it to the literature by the codes from Distal et al. Hussein Mani et al., we notice that our codes outperform or are just as good as the codes in the literature for any rate code. We now verify these results with our Monte Carlo simulations. What we note, we first have a rate 1/5 codes over here. And as you can see, our code performs just as well as the code given by Distal et al. For the relevant frame error rate range, which is about 10%. But when we decrease the rate of the code, we notice that the gap between our codes and the codes from the literature tends to grow, getting about a 0.12 dB gain when compared for the rate 1/10 code. And this also holds when we go to the extremely low rate cases, such as the rate 1/50 code and rate 1/100 code. So what have we shown in this work? Well, we have shown and proposed a new way of representing low-rate protograph-based LDPC codes. We've also shown that this representation allows for a simple optimization of these codes, and that the codes we get from the optimization outperform or are just as good as the state-of-the-art codes. In the future, we should be looking more into, we should do more research on different type matrix designs, as we've only restricted ourselves to this high-rate protograph LDGM code concatenation. I thank you all for listening and have a nice day.